Okay. Sorry for the technical issues. So I will talk about the asymptotics for the number of directions determined by an n by n grid in FP square. So we will use this notation bracket n to denote the set of the first n positive integers. And this is the joint work with Graham Martin and also Ethan White with the next speaker of this conference. So I would like to begin by introducing some notations. So we always use P to denote an O prime, and FP is the finite field with P elements. H2P is the affine Galois plane over the finite field FP. This is just FP times FP, the two-dimensional space of FP. Given a subset U of AG2P, we can always use Cartesian coordinate to represent the point in the set U. And the object we are interested in is the set of the directions determined by the set U. And the set of directions is just the set of slopes, and they live in the projective line. And formally, they are defined to be the quotient of the difference of the y coordinate and the difference between the x coordinate. And it could be an element of FP, or it could be a vertical direction if we have to point on a vertical line. Given a point set U, we are interested in estimating the lower bound for the number of directions determined by the set U. So first, it's easy to see that if our point set U has more than P point, then it's not interesting because we can easily use pigeonhole principle to show that we have all the directions. So we will focus on the case where the size of the set U has the most P point. And one of the fundamental results in the study of the theory of directions is the following result by Willey and Cerny. And Willey proved this result in the case that the point set has exactly P point, and Cerny further extend that for all point set with at most P point. This result says that if we have a set with n point, then there are just two possibilities. The first one is that all n points are collinear, in which case we just have one direction, which is not interesting. But suppose they are not all collinear, then this result says that they actually determine many directions, and they give this bound, which is roughly n over 2. And this result has many applications in additive combinatorics and also number theory. So just to give a quick example, so Roarth and Shriver in 1983 used this result to give a short proof of this result by Wheeling and Mike Williams. And this result came from coding theory. And this result says that if we consider a subset A of the finite field with P square element, such that it contains 0, 1, and it has size P. And for any little a and little b in this set, we always have A minus B to be a square in the field. The A must be equal to the subfield FP. And very roughly, how to prove this? So first, we try to embed our set A into the affine plane over FP. And then we show that it does not determine many directions. So that means we must be in the first case where every point are collinear. So all points are collinear, and that corresponds to the case of the subfield. And this result is also true when P is replaced by a prime power Q, but we have to use some extra tools to prove this. For example, we need to use some tools from Cartesian estimate. Okay. So typically, given a point set U, we expect that it has many directions, and we expect that this is not tight. So in the same paper, Roarth and Shriver actually categorize the extremal case. So they show that if we have a P point set which determines exactly P plus 3 over 2 directions, Then after shortfall coordinate transformation, x must be given by the graph of this particular function. So in other words, if our point set do not have this special configuration, then we expect that this lower bound can be significantly improved. And that was confirmed by Gas in 2003, where he showed that if we are not in this case, then we can improve this constant half by 2/3. In general, if we assume that our point set has some additional structure, then we also expect that the constant here can be significantly improved. In the case that our point set is a Cartesian product, this was confirmed by Di Benedetto, Soimoshi, and White last year, where they showed that if we consider a Cartesian product A times B in a affine Galois plane, then roughly speaking, it would determine at least the size of the Cartesian product. So that means the constant, the multiplicative constant here is 1. Whereas in the Rayleigh-Sarney theorem, this is half. So that's improves the multiplicity constant by 2. And they also observed that this result is tight for some wrong rectangles, but they didn't find any tight examples for configurations like squares. So we might expect that if B is actually equal to A, then we can further improve this. And if we can do that, then we already have many interesting applications. So in this talk, we will focus on the case where A is given by the set of the first n integers, and we try to come up with an asymptotic formula for the number of directions determined by this n by n grid. And we will always assume that n is the most square root p, otherwise the set would determine all directions, which is not interesting. Okay, so let's talk about the set of directions determined by the n by n grid. So it's not hard to see that we are just estimating those kind of fractions A or B, where A and B are bounded in a certain interval. So that should be remind us of the classical problem of counting the number of visible points from the origin in the lattice. So we have this result from elementary number 3 saying that if we want to count the number of co-prime pairs in the n by n grid, then this is given by 6/pi² times n². So that means if we want to count the number of directions, we need to look at those like positive directions and negative directions. So we just multiply this by 2. So we get 12/pi² times n². But there we are living in Q², where the characteristic is 0. But in our case, we are living in the world with characteristic P. So that means some positive directions might actually coincide with negative directions. But this is not the case when n is small compared to P. So in that case, when n is very small compared to P, we can just pretend that we are living in Q². So the same formula applies. If we want to do the computation, we can see that if n is a most square root p over 2, then we have the same formula. So that means the interesting range for our problem is the case where n divided by square root p is between 1/√2 and 1. And to solve this problem, we first, again, try to break our direction set into the positive set and negative set. And of course, it does not make any sense to talk about positive and negative in FP, but we just use this kind of idea. So you can check that for the set of positive slope, the number is exactly 6/pi². And also for the negative slope, it has size exactly 6/pi² times n². But the issue is that a negative slope might actually coincide with a positive slope. So that means A over B is actually equal to minus C/D in FP. And we can try to rearrange that to see that that happens if only if AD plus BC equal to P. So that means the problem is reduced to counting the number of solutions to this bilinear Diophantine equation. Bilinear Diophantine equations are well studied, and typically to count the number of solutions, we use scatter sums. So which basically we want to convert this problem to a problem in estimating a certain scatter sum. And in this case, we have AD is congruent to minus BC modulo P. So we have 1 over P minus 1 times the sum over all dirichlet scatters modulo P, where the summand is given by chi minus 1 times this force moment. We break the sum into two parts, namely the contribution from the principal scatter and the contribution from non-principal scatter. So when chi is given by the principal scatter, it's easy to see that each chi-m is just equal to 1. So we just get n to the power 4 over p minus 1. And if we consider the contribution from those non-principal scatters, there's a recent result by Kerr showing that we have the following sharp estimate on the contribution of non-principal dirichlet scatters. So this is n squared times log p. And usually we think that this would be the error term if n is sufficiently large. So if n is sufficiently large compared to p. So you just need to compare these two terms. But unfortunately, in our case, this is not the case because we are working in a case where n is less than square root p. You can see that this term is actually larger than this. So that means we have to use other tools to find the asymptotic formula for the number of solutions. Our idea is to we first fix A and B. And of course, they have to be co-prime because the right-hand side is equal to P, which is a prime number. So we first fix A and B. Then we know how to solve this standard linear Diophantine equation AX plus BY equal to P. We just need to first find a particular solution X0, Y0. Then we can introduce a parameter T, and then we can write all solutions in this form. And because we need our X and Y to be between 1 and N, then we have a few inequalities. We can see that if T is in this interval, then it gives rise to a valid solution. So we can see that if we fix A and B, then the number of valid solutions is given by N times 1 over A plus 1 over B minus P over AB minus the fractional part of this N minus X0 over B and the fraction part of N minus Y0 over A minus 1. We can sum over all pairs to give exact formula for the number of solutions to this. And we can try to replace this X0 and Y0 by this A conjugate B, which means the inverse of A modulo B. And we also have this. So now we would expect that this would be the main term, and this would be the error term. And the heuristic is that if we believe that our fractional part behave randomly and uniformly, then the expectation of this is half, and the expectation of this is also half. So the expectation of the whole thing is 0. So that means we expect that this will be small. Here we are summing over T. The T is the set of co-prime pairs such that A plus B is at least P over N. Okay, so now we can try to estimate the main term. So for the first sum, we can try to use the Mobius trick because we are summing over all co-prime pairs. So we can use the Mobius trick to convert that to the standard double sum. And then we can use a generalization of integral test to approximate this double sum by a double integral. And of course, we have to make sure that the error term is not too large. And for the second term, we use the same strategy. We use Mobius trick and we convert the sum into an integral. In here, when we are computing the integral, the special function, which is called the delogarithm function, come into play. And the delogarithm function is defined to be the integral of log 1 minus t over t times dt. And I just want to mention that the delogarithm function appears in many contexts in number theory, and it also appears in a related paper where they try to compute the expected value of the size of a ratio set of a random set of the present integers. So it's not surprising that our asymptotic formula also involves delogarithm function and as well as logarithm function. And for the error term, so we have mentioned that we expect that this is very small. So we have to bound them. And the tool we use is to estimate the discrepancy of this sequence. So given a sequence UN, we can define Zn alpha to be the number of UN, such a UN is in the interval alpha beta modulo 1. Then the discrepancy is given by the maximum value of the difference between Zn alpha beta and its expected value, which is n times beta minus alpha. And for our purpose, the problem is exactly to bound the discrepancy. And there's a famous inequality by Eldridge-Turan saying that we can bound the discrepancy by certain kind of exponential sums. And in our case, the sequence UN involves certain kind of inverse and this kind of fractions. So that means when we apply this, we get some kind of incomplete Kusterman sum, and we have some bound on incomplete Kusterman sums, so we can use them to show that the error term is small compared to the main term. So our main result is that the number of directions determined by the n by n grid is given by this formula, which is p times d lambda plus error term coming from the discrepancy. And this function d lambda involves the delogarithm function and also the log function. And perhaps it's best to look at the figure because this is very complicated and abstract. Okay, so this is a figure comparing our bound with the general Cartesian product bound. So for this orange curve, this is the Cartesian product bound, which corresponds to the parabola lambda squared. And this blue curve corresponds to the case where we are pretending that we are living in Q squared instead of FP squared. And this is given by 12 over pi squared times lambda squared. And this green curve is the denote this function d lambda. And we can see that we do improve the general Cartesian product bound a lot. Okay, and finally, I would like to give a quick application of this result. And the result is a generalization of Thue-Vinogradov lemma. So they proved that if A is a non-zero element in FP, then for any alpha, we can always find some x, which is at most alpha, and some y, which is at most p over alpha, such that this equation holds. So we can easily convert this problem into the formulation of directions, because basically we are trying to see what are the possible values of x over y and minus x over y, and they are exactly the directions determined by this kind of Cartesian product. And recently, Soy Moshi showed that so here the product of these two intervals is roughly p. So Soy Moshi considered a case where the product of the interval is less than p, and he showed that we can show that there are at least roughly the product of these two interval, many a, such that we can solve these congruence equations. And in our case, we just set alpha and beta to be n, and we are able to improve that by a multiplicity constant. And that concludes my talks. And, thank you very much for your attention.
Thank you. Do we have